All right, good stuff. Hi, everybody. Hi, as Anton mentioned, my name is Levon, and I work at Agoda. We're based in Bangkok. It's really warm there, and this is my first time in Russia. It's a lot colder than I expected, like really cold. I never thought I'll see snow in April. But I'll tell you this: the welcome was really, really warm. 6 a.m. Saturday, somebody walked into my hotel room, woke me up. It's no joke, really. He walked in, he woke me up, said some stuff, and then just left. I don't know what he said. I didn't understand it, but I imagine it was welcome to Russia, so it was great. So here today, I'm going to talk about matching or matchmaking, and not this kind of matchmaking, although I'm sure everybody's familiar with this. Let me give you a bit of background before I talk about what kind of matchmaking we're doing. So Agoda is a hotel booking platform. So we sell hotel rooms to people like you, people like me. And we work with a lot of different online travel agencies. It's not just our own inventory. We work with Booking.com, a few other players in the market. And what we want to do is we aggregate everything together, combine them, and show our guests the best price, right? It's easy, right? Sounds like a great idea. So why am I here? What's the problem? The issue is duplicates. And by duplicates, I mean you go to the website, you click, I want to stay at this awesome fake hotel, wherever it is, and you see all these 6 entries, and you don't know which one to go to. And that will happen if we work with multiple providers, right? Each one of our partners can have the awesome fake hotel, and if we're not careful, we're going to show all of them. Adds to confusion. And then let's say somehow magically we combine them all into one. Same issue with rooms. You go to the property page, you want to choose one of the rooms, and you see the same room repeated over and over and over again. And this is just one example. If we're not careful, we can have, a gigantic page of the same room. It doesn't give us a good user experience at all. Our customers are going to start going crazy, and they're just going to leave the website. Definitely not what we want, right? So what's the solution? What do you guys think? Matching, right? We take 2 properties and say, it's a match, swipe left. Was it swipe right? I don't remember. Who knows? Nobody's used Tinder? Okay. I think it's swipe right. But anyway, we can't do everything by hand. We used to, actually. We had a whole team who would basically go through all the property inventories of ours and our partners and go through and say, okay, these 2 properties are the same, and then for those 2 properties, the rooms are the same. It didn't really work out well because it doesn't scale. At first, it was just 100,000 properties. It's OK. Now we have more than 1 million. And with 1 million properties, you can't just do that by hand. So automation's the answer. It's always the answer. The question is how to do it. We can't really turn our team into robots and just make them work 10 times faster. It just did not work. We tried, but they resisted. So this is where we come to Cupid, which is our framework for doing this kind of matching, this duplication of rooms. So at its core, it's a multi-purpose classification framework, okay? And by classification, I mean it will say either it's a match or no match, or these 2 properties are the same. So before I talk about what Cupid is and how it's constructed, let's talk about the toys, I like to call, what we're working with. So we have a pretty big Hadoop cluster. I mean, it's significant. It's not the biggest you'll ever see, but we do have around 11,000 cores, 50 terabytes of memory we work with, and 10 petabytes of storage. It's not Google or Yandex, but it's big enough that we can run 20, 30,000 applications every day and still only use 30% of the cluster. So we can do quite a bit of stuff. And what we use to construct Cupid is we use Scala for coding and obviously Hadoop, and we use Spark for our distributed computing, okay? So let's look at what Cupid looks at the very, very high level. This is actually the same for any kind of data processing work. It's just we have this convenient ML step in the middle. So what happens is we take the properties, our partner properties, our properties together. We do some data preparation, do some cleanup, things like that. We feed all of that to the machine learning layer, okay? And machine learning, basically, you train with training examples, then you use the training to find a model. Once you get a model, you apply it to your input set, you get predictions. And predictions are usually not always great, so you have to do a little bit of cleanup ahead of time. And for our case, because we're dealing with properties, if we map the wrong properties together, you could end up in the wrong place without a hotel room. And that's a serious problem. So we can't just trust our automated process. We still have to go through and manually verify that what we found is actually correct. But once everything is done, we store it in a database. You're not going to see 2 versions of awesome fake hotel anymore, and you're not going to see 3 different versions of the same room. You're just going to see the same thing. So it's great, it works. Next is the actual ML layer. I like to call it the magic layer, because if you've never worked with it, you just see stuff going in and stuff comes out, and you don't really understand what happens, but it's amazing. It's like magic. But let's go more specifically about what really happens when we're training. Okay, so suppose our task was to be able to classify images based on what they contain, right? Let's say it's a picture of an apple. This is kind of small. Can you guys see what this says? Is there a laser pointer? Which one? This one? The red one? So this is apples here. There's pears, and at the very bottom, I think they're horses and dogs. So basically, the task here is to be able to classify each of the images by what they contain. So first step, once we get our training set, we already labeled them, okay? So we know that the top images are apples and the bottom images are horses. We do feature extraction, and that would really depend on specific algorithms. Once you extract the features, you apply the labels to these features, and you do your training. And that's really where the magic happens, and you get a model here. Now, the next step is to see how well your model actually works, right? So what you do is you pick some test examples, test input in case this is an apple. You do the same kind of feature extraction that you did here. It has to be the same, actually. It's very important. And then you feed it to your model, and you see what the prediction is. And hopefully, it's going to say it's an apple. If it doesn't, then maybe you need to go back to this stage and fix it a little bit. Now, what's going on behind the scenes, right? Again, it's easy to just look at the output and think everything's great, but really, some other kind of magic is going on. Now, for us, I'm going to talk about how matching relates to machine learning. For us, it's a classification problem. So I'll talk a little bit about classification, then we'll go into more specifics of how we handled it. So what is classification? It's a process by which ideas and objects are recognized. In this case, we want to generate a prediction of what the image is, right? Apple, tomato, cow. And more formally, go back to, I don't know, high school, middle school, where you guys learned about functions and stuff. I don't remember. You have an feature input set, X, and you have output, Y. And the aim is to find a prediction function, F, that will map your inputs to the outputs. Okay? So again, training. This is the step where you actually find the prediction functions, right? So you want to have label examples. This is important, right? Oops, wrong button. So your label examples are things that you know map to each other. You know that x1 maps to y1, x2 maps to y2, and all the way to xn maps to yn. I think probably do this in Excel if you want to play around with it. But this is the important part, testing. You have to apply to never before seen test set. By never before seen meaning if you used 5 mapping to 6, you cannot use 5 again to test, because it's very, very likely that your model would do really well for examples it's seen before, but the aim is to apply to a much bigger set. So if you train on 1,000 samples, you might be applying it to 1,000,000 samples. So it's very important for it to generalize. So during the testing phase, you have to use examples you've not seen before, and you have to check how well it actually predicts. Now, going back to classification, you can think of it as multi-class, which is what I presented, and two-class classification. Okay, multi-class means you can have many different classes, in case like apple, horse, cat, whatever, right? And two-class only allows 2 categories. Usually it's 0 or 1. So apple, no apple, right? It doesn't say apple and tomato. And you can actually think of multi-class as generalized to many, many two-class classifications. So you could say it's not an apple, or it's an apple, or it's not a tomato, or it's a tomato. And you have many of those. You can combine them to get multi-class classification. Okay, I'm impressed. Nobody's bored. Okay, but just to simplify things, 2 class, it's swipe left, swipe right. That's it. So this is the interesting part, right? How do we find this model? And this is where machine learning comes to help. There's a lot of different techniques that exist. I'm sure a lot of you have heard of this neural networks, which is just the hype right now. I think Google came up with some crazy stuff. There's also support vector machines, logistic classification, etc. It's many, many different techniques, and each one of those is appropriate for different scenarios. Let's look at a very simple classifier. It's called nearest neighbor. There's actually no training here at all. The model basically assigns the label, whatever, of the closest test example. In this case, this guy is closest to this square, therefore it's a square. That's it. It's very simple. A slightly more complicated one is a linear classifier. Okay? In this case, basically, it just separates things on the left as apple, things on the right as not apple. Very, very simple. Now, when we talk about any model, I mentioned this before, like generalization. So I'll explain why generalization is important with the fitting of points on the polynomial. Okay? If we underfit meaning our classifier is too simple to appropriately describe all of our test inputs, okay? So in this case, this line, it kind of captures the flow of the points, but it's definitely not going to generalize well. I mean, you have a lot of things here, it doesn't work. And in this case, you have overfitting, where you let a lot of the noise in your input to influence your model. Okay, this actually happens quite a bit in real life. When you apply your test examples, and they're the same as the train examples, you think you're great because you fit every single point, right? This is why it's important to test with examples you've never seen before. Because if you test with things that you already used to build your model, then you're going to think it's awesome. And then suddenly you're going to have points here, 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 and your model is misclassifying them. So here the best one is this degree third polynomial. It kind of captures the flow of the points pretty well. It doesn't capture everything, but it captures the main flow. So, as I mentioned, simple classifiers don't give high accuracy. For hotel matching or the room matching that we needed to use, it definitely didn't give any good accuracy at all. So we need something that works in high dimensions, not this kind of high dimensions. It just means that the feature sets that you use to build your model basically have many dimensions. I don't recommend doing this when you're high. And we decided to go with support vector machines. Okay, it's a supervised machine learning algorithm. Supervised meaning you have to actually tell it. You have to label your input set. You can't just give it a bunch of inputs, say figure out what this means, right? You have to tell it this is a match, this is not a match, and given those inputs, you'll be able to figure things out. So let's talk about support vector machines. Basically, a very simplest, it's a frontier, which is this one, that best separates two classes, which we can call these the greens and the reds, right? And support vectors themselves are the test inputs that are closest to this hyperplane, okay? So how do we choose the right hyperplane? It's actually not quite that complicated to think about, although it mathematically is very complex. You can think of a few rules, okay? The first one I already explained. It's the hyperplane that best segregates the two classes, so that's simple. It's B here. Now, what if you have this case of B, C, and A? Which one is it? Anybody? C, right? Because in this case, it maximizes the distance between the nearest data points, which are the support vectors, and the hyperplane. So these are your nearest data points here, and this is the hyperplane, so that's why C is the best one, okay? So how does this apply to hotel matching? We have two hotels that look like they might be the same. Okay, the name's kind of similar, they have the same star rating. If you don't see the addresses, they're actually also the same. So, and the aim is to say if they're a match, I guess swipe right, or they're not a match. So it's a two-class classification problem. And we did use SVM for it. It worked really well. So how do we use it? So you can think of these pluses as our positive test cases, or matches, confirmed matches, and the negative ones are the confirmed non-matches. This is actually really what it looks like. So we use this, we label them, and we build a model using SVM. That's going to allow us to predict things. So then we need to apply this to our entire data set. So we don't actually have pairs of hotels. We just have properties from one provider, let's say Booking.com. We have properties that we contract ourselves, and we have properties for several other partners, right? So we don't really have pairs. What we do is we generate all possible pairs for every hotel. So we find, like in previous example, Hotel Lapua here, and then we find every other hotel that our partners have, and we match them together. And this generates a very, very massive set. Like, for 1 million properties that we contain, it's like possibly 1 million times 1 million. It's a huge set. We generate all the pairs, and then we use the model that we created to classify all of these pairs. So it's either a match or a no match. Okay? Once we do that, then we have to figure out which ones we actually keep. So let's go back to the flow, very similar to the flow I showed earlier, except now our training pairs are not images, they're actually pairs of hotels. So this is after the data preparation phase, when we grab all the possible properties, we pair them together, and we feed them to the machine learning model. So these are the training examples. We do feature extraction, and I'll talk about that in a little bit, but it's a very important part. Now, depending on what features we pick from these pairs, it will determine how accurate our model will be. Once we apply the labels, whether these are confirmed matches or confirmed non-matches, we do our training, and we get a model. Okay? Next is the testing phase. Now, this is, again, very, very important for us because the possibility of error is high, and when we have an error, it's horrible for our users. Like, you walk in, arrive somewhere at 2 a.m., you go to a hotel, and they don't know that you exist because we messed up when we mapped the wrong hotel, right? Definitely don't want to do that. So we go through quite a bit of training. So actually what we do here, let's say we have 10,000 entries that we know are matches together, right? We do our training to a smaller set, let's say 3,000. We build a model based on the 3,000, and then we apply it to the 7,000. And we want to see how accurate we are. So that's 7,000 our validation set, and the 3,000 is our training set. So what about feature extraction? So I mentioned it's a very important part of the whole process. And depending on which features you pick, actually you get a totally different result. So in this case, let's look at this pair. So we have a Penn Singapore, Penn Pacific Singapore Hotel and Penn Pacific Singapore. You notice that the addresses are the same, but they're kind of different. The locations are also almost the same, but not quite. Same with the name, right? So the features that we extract here, this is just a sample. We actually have 3 times as many. I didn't want to fit everything here. Like, for example, are the names an exact match, right? If they're exact, then that's a pretty strong indicator they might be the same. But even if they're not an exact match, it's still possible for them to be the same because lots of times people put hotel after a name that doesn't need to be there. So then we look at things like we filter common things. Like we filter hotel out, and we filter out the city name, for example. We might filter out even things like motel, star ratings, things like that. And then we look after filtering, are the names the same? So that's another feature that we look at. And same thing with distance, the edit distance between the names, whether the addresses are exact match or the numbers are the same, things like that. So we use all these features to build a big feature vector, which is what we feed here to our training and also to our model. Okay. Now, once we have the model, once we have the features, and we've actually combined all of our properties into pairs, how do we actually use SVM, right? What does it give us? So SVM is great because it actually combines a lot of weaker features to provide a very robust prediction. And by weak features, I mean, like, if you take out hotel from the name, they're a match. That's not a very strong feature. Now, if the hotel names are the same, that's a pretty strong feature. But it's very possible for 2 properties to have the same name, even in the same city. So that still doesn't mean that they're the same hotel. So you have to look at a combination of things to actually decide whether 2 things are the same. So SVM actually provides a prediction which tells you there's like a 90% chance that this is a match, or this is Class A or Class B. And what we found, it didn't really work well for us. So instead, we just went with a simpler metric, which is the distance of each data point to the hyperplane. So because this is a two-class classification problem, the distance to the hyperplane is either negative or it's positive. So a large positive distance means it's probably a match, and a negative distance means it's definitely not a match. And anything that's close to 0, it's kind of murky. You don't know. It's probably misclassified one way or another. This is an example of, let's say you have your Pan Pacific Singapore hotel, and it was paired up with these 4 properties here. Okay? And the distance metric that we got is low for these guys, meaning it's either close to 0 or it's negative, and it's high only for this one. So therefore, it's probably a match. Now, life isn't always this simple. You know, if it was, then a lot of things would be a lot easier to deal with. What happens is we sometimes get one match. It's probably our match. It's great. Other times, we get many matches, which is the more common case. We get many things that are kind of positive. We don't know exactly which one it is. And our model isn't perfect, actually. Doesn't generalize perfectly. Lots of times we have a property that's actually not the same get a higher score than the right one. And that's a problem with our model, and also a few other issues like data integrity issues. I'll talk about that in a little bit. So we have many matches. We have a metric to decide whether it's good enough or not. What we do is we look at the closest 2 positive matches for a property, and if they are too close to each other, we just throw both of them away, right? So we want to have one match that's sufficiently far from everybody else, okay? So if we have Pan Pacific Hotel here, what we want, ideally, we want this guy's distance to be sufficiently further away from all the other guys. Then we can be more confident that this is a match. And of course, if we have no match, it means that either our model's not good or there actually isn't a match for this property. So we just move on. So for us, it worked really well eventually. We got better than 99% accuracy, and we were able to map around 96% of everything that can be mapped, which is a great result. But does it scale? And what we found that when we did it for 10,000 properties, it worked great. It finished everything in like an hour. And we tried it on the full set of more than 1 million properties, and it took 30 hours. And we can't deal with that because we get new properties coming in every day, and we have to be able to run the full set every day. So 30 hours did not cut it. So we were able to scale it down, but we had to keep a few things in mind. For SVM, prediction is very expensive. So every data point that we send to prediction, it takes a lot of time. And when we do million times million, it takes 30 hours. We employed a few techniques, a few heuristics to be able to reduce the total number, because obviously we can't just predict on every possible pair of properties. So we started doing things like we will only pair properties up if they're in the same country. So if they're not in the same country, we just assume they're definitely not a match. Also, we added things like some geoproximity, so they have to be within, let's say, 50 kilometers of each other to consider a match. Now, you might be asking, why don't we just say they're in the same cities, there's the same zip code, or just look at the longitude and latitude? Well, it's because humans are not robots. They're not perfect. They make a lot of mistakes, and all the input that we get from these properties, they're actually all put in by humans. And we've seen some really interesting things, like a longitude and a latitude are reversed. It's actually pretty common. We've actually seen a whole city where everything was reversed. Or city names are different. Sometimes people add in like the state name if it's in the US. Sometimes people put the state after. Sometimes they don't, so you can't really just rely on a city to be the same. Also things like Manhattan. You guys think Manhattan's a real city? Do you know Manhattan? But it's not a real city, actually. It's part of New York. But in some places, they call it a city. Other places, they don't call it a city. So we can't just say, are the cities the same? Because then we'll miss everything in Manhattan if somebody said this hotel's actually New York. So we can't actually catch everything. And that's the downside of having metrics that say they have to be within certain distance to each other, or they have to have the same city or the same country. So what we decided was this compromise. So we run on the larger set less frequently, maybe once a week or so, And it's okay if it takes 30 hours, because on a daily basis, we run it much more regularly. It takes only 20 minutes. And then once we get the run from the larger set, we verify, make up the difference, and we look at things. And usually we catch about 1% extra mappings that we missed before. But it's okay if it happens once a week. The worst thing is our customers just see the same thing twice for a short period of time. So that's Cupid. Thank you. Questions?
Thank you, Levon. Any questions?
Yes. Hi. Hello.
Cenzura. Whoa.
Hi. Maybe it's your location.
Yes, probably.
Just move a little bit.
Hello.
Hi. Are you a musician by any chance?
Probably I'm correct. Hi. Oh, this is much better.
Perfect.
Thank you for your talk.
Thank you.
You said that to find matches, to find duplicates, you need to calculate all possible combinations of all properties.
Yes.
And that would be like a lot of data.
Yes.
And you said that you usually find more than one match, like many matches of same property. And when you're trying to find a group of similar objects, that looks like more clustering problem, not the classification. The question is, did you try to use some clustering algorithms
You're right.
Classification?
If we were looking at it like, if we were to combine everything together and we'll see which clusters are the same, we probably would have used clustering. But initially, the way we started was we only had one partner. So our problem was basically finding all the properties that they already have. And that was basically, we get two and decide whether it's a match or it's not a match. We just kind of scaled that out once we started adding more partners. Now we have a lot more partners than one right now. I think around 10, and it's going to be a lot more later. But you're right, could have been a clustering.
Yeah, you already have this data flow, you already have the feature extraction, so you could just use same features and try running some clustering algorithm on same data set.
Yeah, definitely, we could.
Yeah,
Could do
thanks.
Hi. Does it work? Okay. Thank you for your presentation. And you have said that you deal not only with hotels, but with exact bookings that deal with rooms.
Yes.
Exact properties. So my question is, do you have separate models for matching rooms, and how many maybe SVMs do you need to classify rooms for exact hotel? I'm sure that it is scaling well, but how do you do this, and what features do you use for classifying rooms? And because they don't have exact names as hotels,
Yes.
And maybe something like image matching.
Okay. So let me repeat the question and make sure I don't miss anything. So first question was whether we use SVM to match the rooms, right?
Yeah.
How many do we use? What kind of features do we use? And whether we use image matching, right?
Yeah.
Okay. So yeah, we use the same flow. The algorithm's slightly different. We still use SVM. to match the rooms. You're right, though. Rooms are much more difficult problem than hotels. Actually, the same SVM can generalize really well across different partners, but it does not generalize at all between partners for rooms, right? So if we were doing, let's say, rooms between us and Booking.com, that's one model, and if we do for another provider, usually we have to do something else. And the problem that happens is, some providers, they standardize the rooms. They say they only have, let's say, double room, single room, and executive room. And then the same hotel with another provider gives you a room, flamingo room. You don't know what that means. It could be any of those three, right? And there you just can't do anything. In fact, for room matching, the accuracy is still high, but the coverage isn't quite as good. We have to do a lot more work to make up manually. We've looked into image matching. Again, same problem though. Some people give us great images, and other providers just give us the same image for every room, and we don't know what to do about that. Sometimes we don't even have images. So rooms is a much more difficult problem and involves more manual work. And all the features for rooms come from the name, except maybe for size. And the problem with that size is it's also not correct, by the way. Like I've seen rooms where we know it's exactly the same room. And on our side, it's 50 square meters. On another side, it's 10 square meters. Like really it says 10 square meters. We've also seen rooms where I think somehow they messed up from square meters to square feet or something, because it says like 500 square meters in one. And we know that room is actually just enough size to give you a bed. It's like 20 square meters. It's tiny. So even using a size is not good. So it's a much more difficult problem to solve. There's a lot more manual work involved.
Okay, thank you for your talk. I need some questions. The first one, how did you solve the problem with different order of coordinates, latitude and longitude?
Mm-hmm.
Did you use something outside service like OSM for checking is these two places are same or are different? And the second one, how did you solve the problem with Manhattan and New York and some similar situations?
Okay, so the first question is how do we solve the longitude-latitude reversal, right? And the second one was with the cities. Okay, so the longitude-longitude, because we use many features, it's not the defining feature. So even if the longitude and longitude don't match, it's just one feature that doesn't match. So we have around 20 of them. So we can still, if everything else is great, like if the name is the same and the address is the same, then we'll still get it as a match. The only problem is we will have to catch it in our larger run set, because we can't consider everything that's within 10,000 kilometers of each other. So that one was not a big deal. With the cities, we just same thing. It's just another feature point, because it's not a very strong indicator based on a training set. Now it's important to have a good training set to make that work. If all your training examples, the positive matches have the same city, then it's not going to generalize. So it's important to work with the training set to add cases where it's a match, where everything else matches except, let's say, the city, and then see how well it works.
Hi, Levon. Thank you for your talk. I wonder if you actually have tried the nearest neighbor classification algorithm for your data, and what classification rate did you achieve?
So we haven't tried in production. We've tried testing, and nearest neighbor, we did the same thing. We extracted all the features and then saw which one was the closest and picked that. For simple examples, it works great. It really starts failing when you look at more complex cases where the names are like slightly different, and there's multiple properties with similar names in the same area. That actually happens quite a bit. In those cases, we get horrible results, and we have no way to know whether it's good or not. So we gain about, 20% more coverage by going to SVM, which in our case is like a couple of 100,000 properties.
I have two questions. First, have you used similarity learning? And second, which negative sampling strategy have you chosen?
Can you repeat the first one? Have I used similarity?
Similarity learning.
No, haven't. And what was the second question?
And second, which negative sampling strategy
Which
have
negative?
you
Okay.
choose?
So
And why?
initially, what we were doing were just like randomly generating negative samples based on confirmed positive samples. So, you know, if we know that the Hotel Lapua matches Hotel Lapua, then it doesn't match everything else, right? And we had a 10 to 1. So we had 10 times as many negative samples than positive samples. It was great for most cases, but eventually we realized that we actually need to add in some confirmed negative cases as well, because our model was misclassifying some pairs as mapped, but then when we were looking at them manually, they were actually not mapped, so we started including some specific negative examples in there as well. So our current strategy is basically we generate, based on confirmed matches, we bought 10 times as many negative matches, and then we also add in some specifics.
Hi, thank you for your keynote. I know that it's hard to create all those algorithms, to train, to fix, to keep it going. And my question is, did you thought about using some already existing technologies by some other companies like Google, IBM, or whatever?
So we looked at crowdsourcing actually to help us work through it. That's the one we've gotten the best results with. There's a lot of them out there. Crowdflower is one of them actually. We do partner with them sometimes for some difficult examples, but at the end of the day, we got pretty good results, so we didn't really think about going elsewhere.
Hi, thanks. You improving your algorithm and your decisions about what hotels is the same or not are changing. No.
Well, our classification
they
changes,
changing.
yes, possibly.
So how these changes may affect the users and what you do with that?
So as I mentioned, because matching properties is such a important thing, if we get it wrong, then our users really suffer. We don't put anything in there unless we verify manually. So before, where we had to find matches, now we just verify that they're actually correct. So there's still a manual step involved. It's just a lot smaller than it was before.
You moderate all decisions.
Yes, we have to. Once we get the final set, we go over it manually. And once we confirm something to be a match manually, then we don't have to look at it again. So really the problem boils down to, even though we run it on the full set just to make sure that we catch the accuracy correctly, it's still only whatever new properties that we added. So if we add, let's say, 50,000 in the next week, then we only really care about those 50,000 properties. Once we run them through and manually verify them, then we're not going to change them. Even if the algorithm thinks it's different, then that's just a data point for us to do further optimization. Because eventually we want to be confident enough to just never do any manual work, right? We want to just say we're 100% confident it's a match. It's difficult to get there.
Thanks.
I think it was the last question. So if you have many others, you can find the one in the expert zone. And thank you again.
Thank you.